Hello, community! Self-improving AI agents. Hey, that sounds interesting. So great that you are back. So let's talk about self-improving AI systems. And you know what is the beauty? No humans needed. The machines will optimize themselves. So how we do this? Let's open up this video. And of course, self-improving AI models here have garnered some increasing attention here in our community. Especially they have the potential to enhance their reasoning capabilities through simple mechanisms like iterative feedback and some refinement. So let's look here at AI systems on their most elements level here, large language models, before we move on to the agents. If you're not really familiar, I recommend here some papers to you. And this here is from October 2024. Can grow into reasoning generalist via self-improvement. And here some self-correction reasoning, University of Michigan, LG AI Research, and University of Illinois. And then we have more or less two options. Now, if you remember, we can either employ bootstrapping strategies here by leveraging self-generated rationals for our reasoning paths. And here we found here that this is a very nice publication, July 2024, UC Berkeley. Or if we introduce here a self-refinement mechanism through the reinforcement learning, R1 is the best, the most famous example here. But of course, don't forget the other literature. A year ago, we had here this beautiful publication, IBM Research in University of Pennsylvania here. Or if we go here from June 2024, improving LLMs via fine-grained reinforcement learning with minimum editing constraint. So if you want to have a little bit of a history, if you want to understand how it came to be, these are papers I would highly recommend. But of course, talking about recommendation, now we have to move now to agents, no? And you remember just here exactly, a month ago, we were talking here MIT, Harvard University, Stanford University, Google DeepMind about multi-agent fine-tuning with the topic of self-improvement here, especially here for more complex reasoning chains. And if you remember, we were building a multi-agent system, and we told here that fine-tuning with independently specialized agents that interact to generate diverse reasoning chain. This was really a fascinating topic in AI research just a month ago. You have here the project website, you have here the GitHub repo for the code. But if you don't want to read this, no problem, because I have a video, 22 minutes of pure information for you, multi-agent fine-tuning from Harvard, Stanford, MIT, Google, and DeepMind. So we know here a basics, and now I think it is time here to start the video. What we need a spark. We need a spark of genius, or, in our case, we really have a guiding star today. And I mean, what does you mean with star? Star. The self-sort reasoner, bootstrapping reasoning with reasoning. And you might say, unbelievable. And maybe you forgot it. Stanford University, Google Research. This is already from May 2022. But the idea of STAR was something beautiful. And we're going to focus on this today because this will be a building step for us to go here to the next level of the complexity. So if you remember, STAR provided here a foundational concept of bootstrapped reasoning. And of course, this was only valid for single agent system. Yeah, of course, it was 2022. This was a method designed to enhance the reasoning capabilities of our LLMs for the complex task. And the core idea was to enable the LLM to learn to reason better by training on its own successful reasoning attempts. And I told you at the time, hey, this is a beautiful example of bootstrapped reasoning in action. So let's do here a short interrupt because bootstrapped. I remember in my last video, you, as a subscriber, you always ask, hey, explain this bootstrapping in AI a little bit more in detail. Now, it is rather easy. Bootstrapped here, if you're not in the American English-speaking world like I'm here sitting in the heart of Europe. So I thought, where the hell does bootstrap come from? It is borrowed from the phrase to pull oneself up by one bootstrap, which implies achieving something difficult or almost impossible by one's own efforts alone. So, beautifully. Now, this means if you apply this to reasoning, we have more or less a cycle of reasoning, evaluation, and learning. to give you two simple examples of bootstrapping in AI that you know that you're familiar with. The first one is curriculum learning, no? Or the self-paced learning, where you gradually increase the difficulty of the training example as the model learns more and more complex stuff. Bootstrapping. Or, if you know the game AlphaGo, self-play in reinforcement learning. Yeah, exactly. Remember here the agent that played here games against itself? It may sound a little bit strange, but you know exactly this is it. The outcome of the self-play games, either you win or you lose against yourself, provided here a beautiful binary reward signal. And our reinforcement learning algorithm used this reward signal to update the agent's policy, making it play better in the next games. So you see, bootstrapping was always with us. This is not something completely new. Okay, end of the interrupt. We are back on topic. So let's talk here about star. And star, you have more or less two options, if you remember, without the rationalization and with the rationalization. So what we do, we have a pre-trained LLM, an initial data set of problems with some given answers, and our technique starts with a small prompt of examples with intermediate rationals given. And we assume that some of the rationale lead to the correct answer and are of better quality than those that lead to incorrect answers. And therefore we take those better quality answers and we started to fine-tune our LLM, our base model, on this specially, if you want, filtered data set. And then with the new, now supervised fine-tuned LLM, we restart the whole process. And we find out, hey, this is really nice because this could here improve the performance. And if you wanted to have this a little bit more with the total expected reward across the complete data set, we had this. And for the gradient here, we had a simple standard log derivative trick here for the policy gradients. And you remember, this worked reasonably well, but with one exception. Of course. And now we come to start with rationalization. And at the time we find out here that the rational generating bootstrapping algorithm, it carries here a certain limitation. And since the model is only trained on the example which it answered correctly, the improvement suddenly ends here when the model fails to solve new problems. So therefore, there is what we call here a new technique that was invented here by the authors of the paper called rationalization. And it is rather easy. It is a trick if you want, yeah? And as we have seen, they provide now an answer to these new problems. And they say, hey, this answer is now just a hint to the model. And we simply ask the LLM to generate rationals, now in the same style like it did before, in the previous rational generation steps. And given now the answer, the model is kind of able to reason backwards, since it's know the answer, so it's going here back and back and back, and hence more easily generates here a rational that leads to the correct answer. And then we just delete, if you want, this hint. So we have achieved that the model, if you want, itself learned here, reasoning backwards, a solution. We re-engineered here the solution, but we had to provide the correct answer in the first place for this new domain knowledge or for this new complexity. Not perfect, but it was working. If you want to see this here in a pseudocode, beautiful, and here in blue corresponds now to this rationalization, so this step 2 in star. If you want this a little bit easier, if you want to see this here written down, no problem. So we have 3 steps here in star. At first, give them a set of complex questions, star prompts here in LLM to generate answers, using here our classical chain of thought approach. And those chain of thought prompting encourages the LLM to explicitly write out its reasoning step before arriving at the final answer. And this makes here this beautiful transparency in the reasoning process so beautiful. And of course, if we do it multiple times, star might generate multiple reasoning paths, and then we use beam search or diverse sampling or whatsoever. Now we just have to verify that all of this or some of these generated answers are correct. So we select here the best answers, compare against the known ground truth. You can have either a second agent, you can have a human that verifies this, or whatever metric you want to establish or methodology. And then if we have the correct answer, then it is easy. We just use this as a data set here to continuously supervise, fine-tune our LLM. So beautiful, our model gets better and better because, this is part C, this process is repeated for multiple iteration, potentially leading to even better reasoning and subsequent iteration. So computational expensive, but maybe with just a little bit help from the human side. So let's come now to the core new idea. We will use this idea from Star. And you remember, Star was only working for a single agent. So what is the logical next step? Well, you got it. Well, in the next step, we will also have this idea of bootstrapped reasoning. So this self-learning is happening now by our configuration of multiple agents. So we simply go from a single agent to a multi-agent system. Couldn't be easier, no? What should happen? Because now, the concept of selecting and retraining here, now the successful reasoning path in Star, it is kind of what we want to do now if we go to higher quality reasoning trajectory that are now trajectory here of multi-agent trajectories of our multi-agent system. And now each of our agents has a different specialization, but is also able to solve certain complexities in the query. So now you see, oh, wait a minute, we have now a little bit more of a complication in this, because we also have here not just the expertise of a single agent, but also how those agents communicate. So what we do, if we have this, we use again supervised fine-tuning here as the primary mechanism for updating here the models. In Star, you remember, we used to train here the LLM on the successful single agent reasoning path. And now in this next step, we will also use supervised fine-tuning to train now each agent in our multi-agent system on the successful interaction trajectory in the complete reasoning process. So you see, just going one level up from single agent to multi-agent, the complexity almost quadruples because now the complete interaction trajectories optimization will also be essential. But otherwise, they're here more or less the same idea, no, to tackle here more complex tasks that require a little bit more sophisticated reasoning by our multiple agents. Again, Star focus on enhancing reasoning in a single agent, and the next step are multi-agent collaboration and a communication that will be the minimal set of a communication necessary to solve the query here successfully. So let's look at the facts here. A simple example. We are in science, we are doing here some hard reasoning, so beautiful. We have a team of AI agents, no? And in the human world, this would be a physicist, a mathematician, and somebody who summarizes here all the scientific work, and they work together to solve here complex problems. And the agents here, in our case, use here, of course, we are not rule-based agent, but we are AI-based agent with an LLM at the core of the agent for reasoning and for the communication. Now, this is a little bit more tricky because it is hard to know exactly what agent should learn what to improve the team overall performance. And otherwise, it could be that the agent have the knowledge and did found the correct solution, but was not able to communicate a complete set of all parameters and a complete set of all the insight into the solution so that the other, let's say, agent, like a mathematician, a mathematic AI agent, could then really start to calculate the formulas where the theoretical physicist came up with. So you see, complexity increases here. And really important, we have now a reward signal only, hey, the team succeeds or the team simply fails. So it is not clear here what agents' actions here are responsible for what. So the key to success or failure is not as clear as we would hope for. If you would like to see this here in a beautiful drawing here by the authors here from Stanford University, this is it for you. This is a beautiful paper, February 7, 2025, Stanford University, Self-Improving Multi-Agent Systems via Bootstrapped Reasoning. You see, we have this basic idea of Star, and we just apply it here to a multi-agent system. This is all there is. Now, this new method, also think about it, it really prioritizes here collaborative optimization, and we have a new element, a shared experience library. And it makes sense if you have multiple agents and you learn something not for one agent but for multiple agents, yeah, you want to store this knowledge because maybe you can reuse it later on, thereby enabling here the agent to collectively learn from and refine successful reasoning trajectories. But note that our reasoning trajectories are not single agent trajectories, but the complete reasoning trajectories for the complete multi-agent system. So there's a lot of things that could simply go wrong. Isn't that interesting? And you might say, hey, that sounds somehow similar to one of your last videos, and you're absolutely right. Because in my last video, I showed you here exactly, we did not have here, what it is called, a shared experience library, okay? But in my last video, I showed you that we built here a knowledge graph. And we put the knowledge graph here in the dynamic memory of the agent. And then, in the second part of my video, that where I said, here, I have some ideas of my own, I told you we have to update here the memory, whatever is now in the knowledge graph, whatever is now, if you want, encoded here in the dynamic memory, maybe we should update this here and bring it to the test time preference optimization. Remember, in the training time compute, we had DPO, and here in the test time compute, we have TPO. So it is kind of similar. Here, the instrument, the tool that we used to record our knowledge was a knowledge graph, and now we have a shared experience library. Beautiful. Interestingly, doing this now, the authors found that this SiriuS idea is working rather beautifully. And they use this here in adversarial games like resource exchange or multi-term, ultimatum, or buyer-seller negotiation. If you know it, great. If not, never mind. It was just able, this system, to learn some robust strategies and not only improve the win rates and payoff or whatever. And also, if you have actor critique variants within the SiriuS was able to show, hey, this really helps, this self-learning really helps here in the role specialization, in the advanced specialization, given the dialogue, given the critique that I have, the forward, backward augmentation between actor, judge, and critique. So there is the performance in this system, which is beautiful. If you want to see this here in the original drawing here by Stanford University, here we have it, problem solving, and here the task is college physics or college chemistry or medical Q&A. So we have here a particular structure. Then we have, for example, here auto critique or competitive, player 1, player 2. Here you have it again, research exchange, seller, buyer, ultimatum. And just would like to focus your attention here on the reward for each single agent. In the normal problem solving here and the complexity that we have for the reasoning path, we have a final output correctness. This is our reward signal. And it is the same in the actor critique, and here utility function value. And you say, so this kind of SiriuS idea builds here a library of successful teamwork. And when a multi-agent system solves the problem correctly, SiriuS now saves the entire sequence of the interaction and the entire sequence of the reasoning steps from each and every little agent that communicates with the other agents that led to that particular success. And you can think of this simply as collecting here the best practice here for teamwork. So this is rather similar to what humans do, no? But do you see what I want to tell you next? Exactly. In this video just 4 days ago, we talked about this. And we said, hey, if we program our agents to improve their reasoning for newer inference-based reasoning, I showed you QNet or QLAS. And in this video, I showed you, hey, normally we wait for the final reward signal at the end of a thinking process, no? But we can improve this because what we don't want to wait till the system finishes and tells us, no, bad signal or whatever. We want to have the power to understand here, if we have a Monte Carlo tree search algorithm that builds our tree, our decision trees, we want to be able to go in with a process reward model on each single decision that the agent is performing in its logical reasoning chain. So therefore, in this video, I showed you Monte Carlo tree search process reward model, new update that we do not have to wait for the final reward signal, and the calculation I showed you was easy. It was a modified version of the Bellman equation. You find all the details in the video. And then, just 2 days later, I showed you here, again on the topic of multi-agent optimization, that normally we would use here for the prompt engineering and the prompt optimization DSPy, but I showed you we can use now topology DSPy. And I call it here prompting the swarm, of course, multi-agent, and we had here DSPy as the, if you want, optimization framework. Now, if you remember, DSPy in this video I showed you there's even something better than DSPy. This is called TextGrad. TextGrad is easy to understand. It optimizes the prompt for each agent in a multi-agent system and a framework by backpropagating a natural language feedback through each interaction. And this is an automatic differentiation. Here, this is done via text. And if you want, there are 41 minutes waiting for your pure delight. Now look at this paper from Stanford University now, February 7, 2025. Do you know what they do? They say, yeah, that's a good idea. Let's compare SiriuS to TextGrad. And this is what I love this idea. Look here at their performance data and their benchmark data. Now, unfortunately, they used here with GPT 3.5 Turbo. I mean, it doesn't exist anymore in 2025. GPT-4 Omni Mini. They go here for what we call a non-reasoning LLM. So it's not like a DeepSeek R1 or an O1 or an O3 mini high or a QWQ32B, but we go here with the classical non-reasoning language model. Okay, never mind, let's do this. So we have here physics, we have chemistry, and we have PubMed Q&A. Now let's look here at the different things. TextGrad, just showed you here, has, let's go with physics, let's say 43%. SiriuS has 46%. So 3.7 percentage point more. Okay, so maybe I would have expected an even better performance than TextGrad. But you know what? If I compare this to Star with 42, it looks now interesting because the jump from Star to TextGrad is not really significant. Yeah? And look at chemistry. The jump from Star to TextGrad is even a negative performance. So this is now something interesting, and chemistry in itself is kind of an outlier in our benchmark data. If you compare this, and medical Q&A is again better. And again, Star with 69, and here TextGrad with 68. We also have a decline if you use TextGrad. So this is something interesting. I have to find out why this is happening, but interesting to notice. But never mind, we have to focus now on the new idea, SiriuS. And let's go here with GPT-4 Omni Mini SiriuS. You see against TextGrad, yeah, it's a little bit. But here in chemistry from 44 to 60, this is a significant jump. But then again from 68 to 73, well, not so famous, no? So, interesting. And you might start to think, why is this the case? Now, do you remember I told you with SiriuS, we have to start somehow. We have some initial condition, and of course, we have to provide the system and train the system on the perfect reasoning chain, the reasoning path here to find a solution. Now, it could be that in your particular domain, in your domain knowledge, physics, finance, whatever, wherever you are, there are only a limited set of examples where you have the perfect reasoning waterfall. No? Plus, remember I told you in SiriuS we have also that some of the reasoning chains that are not really working, we don't throw them away. We keep them and we ask either a human or another agent to optimize here, find a mistake, and optimize here or correct here to the correct reasoning path. And then we put it back into the system and we put it back into the supervised fine-tuning. And yeah, I have to tell you, the authors tell us here they use the OpenAI fine-tuning API for the supervised fine-tuning here when you work with SiriuS. So the official OpenAI structure, nothing could go wrong. So this is now, I think, an effect here of the quality of the training data. Let's come to an end. Let's see what we achieved. We have found a new system by Stanford University. This now is a multi-agent system. It is self-improving in its reasoning, and it uses here Bootstrapped reasoning framework that we know from Star. It continuously, if you let it run and run and run, improve here the agent policy by harvesting here the successful interaction trajectories. They put all these successful reasoning trajectories and the communication trajectories into our library that is available here for each and every agent. Maybe they put it in a, I don't know, in a database or in a memory structure or wherever. And they use here these suboptimal trajectories. They use this that did not work. They have a feedback loop either with a human or with another more intelligent agent. And then they correct these suboptimal trajectories. They augment it now with the human knowledge and say, hey, here happened a mistake. If you do this and this and this, then you have the perfect logical waterfall. And then we put it back into the supervised fine-tuning. And I think for the supervised fine-tuning, we need quite a lot of data. And maybe we have not achieved here the optimal equilibrium here of the pure amount of the data set and the quality of the data set. But yeah, we have to find this out in the next weeks and months as we will test out SiriuS. And here now the end, always here the final word. So the authors themselves, quotation mark, and the authors of SiriuS from Stanford tell us here, our approach enables agents to refine here collaboration strategies without explicit supervision. And this experiment showed that SiriuS really improves the performance across college-level reasoning, the biomedical Q&A, and even negotiation task, if I've shown you here the different settings where we have critique, actor, judge, and so on. So really interesting SiriuS. Gives us a lot of new stuff to think about, a lot of new ideas for how we can optimize SiriuS itself, where we have to position it here in our multi-agent learning framework that we have. But the idea that it even outperforms TextGrad, this is a nice challenge. This is something that interests me. So maybe if you too are interested in more of those videos, more of those explorative AI research, hey, why not subscribe? And who knows what will be the topic of my next video.